I realized last time I totally forgot that we had a quiz, and I forgot to go over it, but I did read your answers, and it seemed like everybody did just fine on it. So the first question, I'll go over the three here briefly. We've beaten to death in class. Intercepts, thresholds, and B parameters are all different ways of saying how difficult an item is. They differ in what they're relative to. So intercepts and thresholds are both expected something when theta is 0. An intercept is expected higher category. A threshold is expected lower category. So I say that deliberately because it's 0 and 1 if you're talking binary data, but it's higher category versus lower category if you're talking categorical data, which is what we've been doing. Whereas B is relative to a logit or probative 0 instead. It's the amount of trait needed to have a 50-50 probability, which corresponds to logit 0. Everybody got the second one, thank goodness. How do you decide when to use CFA or IRT-IFA? One clarification on terminology. It's not necessarily the problem that the responses aren't normal. It's that when you have responses that are bounded, a linear prediction of those responses from the factor is implausible. That linear prediction has to shut off at the boundaries of your scale. So that applies even if you have ordinal data or if you have continuous data that has boundaries in some capacity. So it's not so much the distribution, but the linearity relationship that becomes problematic. And IRT and IFA models posit a nonlinear relationship between the trait and the responses such that it shuts off at the boundaries of the scale. And then last but not least, absolute fit. When do you get it? Limited information only. Did you have a question?
Yes.
Sure.
When did you ever have data that didn't bound?
The only example I can come up with is response time, where you could take as long as forever in one direction. In theory, it's bounded by 0, though. But in practice, most trials where you have some amount of time to respond to something are still going to be shut off after some point. So I can't think of anything. I think the question is whether the boundaries are hit in practice or whether most of the data is towards the middle of the possible response scale. But yeah, I can't think of anything, honestly. You use IRT if you have ordinal data. Ordinal or nominal, categorical, broadly construed. So the numbers are just labels in that case. It's not that 1 versus 2 is what matters. It's strongly agree versus agree, something like that. That's the type of data that IRT and IFA models are designed for. People use CFA models on that type of data, but it's always going to be at best an approximation and at worst totally wrong.
Right. I'm just wondering why you would ever use CFA.
Why? Because it's easy. Because it's easy to estimate those models. That's why. It's a tradition that started in the late 70s was when software was able to actually do this. And because multivariate normal makes so many things easier, people just sort of pretended that that's what they had. And the first CFA models were estimated on subscores. And then the trait would be formed by like 3 or 4 subscores, where they added up all the items to get to something that was approximately normal-ish or more continuous. And then they worked on that. And then in more recent decades, they've started fitting item-level models. But yeah, it is rarely the case that the assumptions proper of a CFA model will hold for practically speaking response types that we see in like psychology and any kind of like scale where you have numbers. Even in cases where people try to be more continuous, like if you have like a feeling thermometer or something like that, you still have an endpoint. And if people really hate something or really like something, you're going to run up into the same sorts of non-continuous boundary issues. I don't know if that gives you a good answer or not, but it's because it's easy is really the answer. It's easy in terms of estimation.
But theoretically,
it's at best an approximation to the truth. It will never be better in the sense. That's where you get into sort of the nuances of estimation. Well, if you have, say, a 5-factor model that you want to fit, and you have two choices, you can either have full information maximum likelihood pretending that a linear model works, or you can have limited information for the ordinal model, which then makes additional assumptions such as missing completely at random. So there's been a whole lot of research comparing sort of if you can't do it the most rightest way, what next? And it depends on a bunch of different things, as you might imagine. In smaller samples, limited information, I think, has been shown to work better than full information maximum likelihood in the context of IRT and CFA, because it's less data demand. Other questions? So then last but not least, yes, limited information is when you get fit statistics. The idea is that they first summarize the item response patterns into either a tetrachoric or polychoric correlation matrix, and then they run the CFA operations on that matrix. So you end up with an estimated H1. It's their best guess as to what the best model is, and we can compare that with our predicted model from the factor structure. So the very end of example 6A, I have those models under WLSMV. So we'll look at those real quick since we're on the topic. I am on page 6 of example 6A. So just to remind you that when you are in the world of WLSMV, if you want to test any kind of nested model comparison, such as 1 factor versus 2 factors, or 1 factor where all the loadings are different versus 1 factor in which they're all the same, which is this example, you can't look at the chi-square values and do the math yourself. You have to let M+ do it via diff test. Always bigger model first in terms of more parameters. So you would save diff test equals, and then name a file for the bigger model, and then take that same file name and add it to the analysis section for the to-be-compared model. And when you do that, you get a chi-square test for difference testing. That is your nested model comparison. So it's nice in that you don't have to type numbers into Excel or otherwise do secondary calculations, but you do have to remember the order of operations and add the lines to your syntax to do that. But here is where we get fit statistics then, because it's relative to that summary matrix. And we also get residual correlations, meaning residual discrepancy correlations as to how well the model fit. So my typical practice in this world is to run limited information estimation first, just to get a decent sense of fit, and then go back and run whatever I've done in ML if at all possible. That way I can use factor scores that have better properties from ML, or otherwise have a little bit more confidence in my estimates than what limited information might give me. My recommendations as to what to do may change within the next year or two as these models continue to become more readily available and people are working on faster and better ways to estimate them. So it's a work in progress, let's put it that way. And I have words, so you can describe that back and forth process if you ever decide to use it. All right. So, questions on any of that? All right, then let me return back to this little spreadsheet that we built last week, because we're ready to move on to the next 2 sets of choices here. So we're talking about categorical item responses. They can be ordinal, they can be maybe ordinal, or they can be nominal, meaning not ordered whatsoever. The models that we just looked at in M+, what's known as a graded response model, that is the one that takes the entire response continuum and divides it into a series of binary submodels, these ones right here. So at each step, all of the item responses are being used. That makes these models relatively stable in situations in which you don't have that many responses in a particular category. It is somewhat hard to explain because of the way that each category gets used, but these tend to be by far the most common options for Likert scale type responses. They do assume that your responses are ordered, though. So what if you're not sure about that, or what if you know that that's not the case? Here are two other options. We're going to start with this one here, and I'll show a couple slides about that. This is what's known as partial credit. So if I have 5 options, I still have 4 submodels. The 4 submodels are still going to share a loading or discrimination, but the way that the locations are defined is different. These are what's known as steps rather than Bs. So the first submodel is, given that you answered 1 or 2, what is the probability that you answered 2? The second one is, given that you answered at least 2, what's the probability that it's 2 or 3? And so it's a series of adjacent descriptions that I think is more intuitive, but it doesn't make any assumptions about non-adjacent categories. So there's nothing in this that stops 1 versus 2 from being higher than 4 versus 5. So let's see what some pictures that I made that looks like this. The original partial credit model was a model that had all of the loadings be the same. The version in which the loadings differ across items is what's known as generalized. But it looks the same in concept. We still have this theta minus location, A sitting out front. The difference is in what those location parameters are defined as, which is just the point on theta at which the next category is more likely. So it has nothing to do with 50-50. It's just the point at which the next one becomes more likely. That's what these mean. So here's an example then that would come from a partial credit model. This is a 4-category picture here. So the probability of the first category is given directly by the first submodel. It's 1 minus that, since it's the probability of the higher one. The next one is given directly by that submodel, and so on. But the difference, then, is that what happens if you drill down into these locations. So the first one, if I go blue to pink, that happens right here, the one that's labeled 0, 1. The next step up is pink to yellow. That actually happens before blue to pink, according to this model. So this is what's known as a reversal. It means you need less of the trait to pick 2 instead of 1 than you needed to pick 1 instead of 0. So that means one of 2 things. Either 1 didn't happen very often, or you have your ordering wrong. That's difficult to do in thinking about that as like a personality type item, but you can imagine it in an educational setting where you literally get partial credit and you can solve so many steps correctly. If the steps are not necessarily ordered, it might be easier to solve one step than another and you're not sure which order to put them in. This would be the type of model where you can actually test whether or not these things are ordered. So the first step happens from blue to pink. That's the point where pink becomes more likely than blue. The second step happens from pink to yellow, where 2 becomes more likely than 1. And then the last step is from yellow to, let's go teal, where 3 is more likely than 2. But the reason that 1 is out of order here is that there's no point at which 1 is most likely. So 1 is not a very helpful option in this example. Here's some data from my dissertation. I fit a partial credit model. I have the done kind. But this plot, which I forget the program that gave this to me, it's an old school plot, maybe Parscale or something, whatever they had in the 90s that we had access to here at KU. This is exactly what you don't want to see. Why is this terrible? Well, I took a continuous variable, which was response time, by the way, and I carved it up into groups. Why did I do that? Because that's what I thought you had to do to fit an IRT model. I didn't know that you could rearrange other types of models to be IRT-like. So this was the state of my knowledge in 2003. I now know better. But what happens when you look at each of these plots is that green is most likely from the lower half of theta, which means that they did not find the picture they were looking for in time. And then it switches right over to black, which means that they found it right away. So this was a search task in which they only had so long. And it looks like people either found it right away or never found it at all. These middle categories are functionally useless, and they're just crawling on the bottom of the screen for each one of these. They're never the most likely ones. So this is an indicator that my categorization was not terribly effective. Here's another example. These are some data that I fit in helping someone with a grant proposal. This is the General Intrusive Thoughts Questionnaire, where there were 5 options, and I plotted the range of step values. So this is more intuitive, I think, to present than the graded response model that we looked at last time, because each of these blue dots is the amount of theta that you need to go from strongly disagree to disagree. That happens around -2 standard deviations or so. Next is to go from disagree to neutral. That's the green dot, followed by neutral to agree, which is the orange triangle. Now these ones you'll notice here, this indicates that people are not using those middles very effectively. They're right on top of each other, and they're reversed in order in a lot of cases. So people are not picking the middle ones very much, or they're not picking them as reliably as they are the extremes. In contrast, agree versus strongly agree is clear over here, and so as a consequence that this scale, that these items cover between -2 standard deviations and 2, this is the latent trait distribution you get. So it does a pretty good job differentiating people because it has information all along the way. Compare that to this picture. So this is an event-specific intrusive thoughts where there were only 4 options. Not at all, rarely, sometimes, or often. The bottom of the scale is compacted between -1 and 0 here, and they're right on top of each other. In contrast, sometimes versus often is the only one that shows any differentiation. And because we have basically no information past -1, we get a giant pile of people at the bottom there. So I don't know how to fix the lower end. How do you do something less frequently than not at all? Can anybody think of a phrase that might be less than that? Can you have negative behaviors? Probably not. You might need some more items that measure lower level things. I can think about how to fix the top end though. What's more than often? Always, almost always, most of the time, take your pick. So in this case, it looks like they could do a better job potentially of defining what the lower 3 categories are to make them more separable, or just only having rarely, for instance. There's another version of the model that holds all of those differences between thresholds or submodels constant. That's called the rating scale model. That one I haven't ever had the chance to use before, but that's about it. So partial credit is going to show up in the example that we're going to do next because it's going to be used in constructing a semi-ordered scale. So partial credit here is a constrained version of this last one that we're going to spend the rest of the time on today, nominal. Nominal is for unordered categories. It is parameterized differently across programs, but the bottom line is that one of the categories is usually termed the reference, and each submodel is relative to that. So in this case, 5 is the reference. The first submodel is given that you answered 1 or 5, what's the probability that you picked 1? Given that you answered 2 or 5, what's the probability that you picked 2? The thing that's special about nominal is that not only do you get these locations where each one would be more likely than the reference, but you also get separate item discriminations for each of these submodels. So instead of having 1 slope, 1 discrimination, 1 loading, you would have 4. So this model takes a lot more data to be able to estimate everything. But you can rearrange the partial credit model into fitting this model. Because if you can specify the model, for instance, as 1 versus 5, and you know what 2 versus 5 is, then the difference between 1 versus 5 and 2 versus 5 works out to be 1 versus 2. So we're going to exploit that trick to show you what happens then in fitting data where you have not applicable answers. So I'm super excited that we were able to figure out these models. So with that said, I am going to turn things over to Jihan, and it's your turn to come talk. He built us a nice little handout. So he's going to go over the nominal response model and then also the semi-ordered model. I'm going to give you the little remote. Clip it to you. There you go. Ta-da! And I will probably still interject because I can't help myself. So I'll let you do it.
Okay, so today we will introduce a new model which will fit in the ordinal response with NA category. And first I want to describe a little bit of nominal response model so that you can have a big picture of like the parameters of the nominal response model. So nominal response model, as Lisa said, is models for polytomous data whose response are not ordered. So here's an example. The item is which political party would you identify yourself with? So you can choose the Democrat or Republican. So these categories are not predetermined orders. So, but you can fit this item to nominal response model to have like the slope and the intercept for each category. The parameter will be in M+. M+ will automatically set the first category as a reference, highest category as a reference, so that, for example, the category 5 will be the reference, and each category will compare to the reference to estimate the slope and intercept. And so for the parameter in nominal response model, there are k-1 slope and k-1 intercept for k option items. For example, if this item has 5 categories, there will be 4 unique slope for this item and 4 intercepts. There are 2 identification methods. For example, you can set the reference categories slope and intercept as 0. Or Bork, who is originally introduced the nominal response model, he used the constraint that the sum of all categories slope was constrained to 0, and the sum of the intercept was constrained to 0. So here's a real data. Because R and M+ will have the different models for nominal response model. Here I show the R how to treat the nominal response model. Here's the first paragraph. This formula is for nominal response. For category K, the probability of choosing this category will be like this. The denominator is all categories together, and the denominator is this specific category. So this model is also called the 1 divided by all model. And we can see the parameter. There are 4 slope and 4 intercept. A1 here is the author of the Mer package called it the overall slope. Overall slope for this item. And to be identified, the first category slope was set to 0. Other categories slope will will be estimated, and the reference category is intercept was also constrained to 0. And in this model, the AK term actually means the ordering of item. As I said, the nominal response item was not predetermined. The order is not predetermined. But if you fit the nominal response model, you can actually get the latent ordering for each category, which means as your in the trade scale, as your trade higher, you are more probably choose one specific category. And for example, this item, the comfort item, the AK1 is the lowest. AK2 is the second lowest. So the AK1 represents option 2. So the order would be option 2, option 3, option 1, and option 4. We can look at the category response curve. So we can see the order should be 2, 3, 1, 4. The 2 is the purple. Can you see that? The purple one, the purple line, and the second is the green line, and the blue line, and the last one is the red line.
So what is the number that goes each one? Oh, what is it? I'll put it in your hat take it. There we go. Let's look at the technology.
Okay.
Yeah, so like P1, the first option, is never the most likely at any point in theta. People low in theta, though, are more likely to pick 3 than 2. And if you're high in theta, then you're likely to pick 4.
Yeah.
P1 is more likely than P2 and P3 later on. Yes. Yes, that is true. But it's never the most likely. Oh, okay. Yeah.
Yeah.
So another use that these models get is to look at distractors in multiple choice tests, where you can see, like, are all distractors created equally well? Are people who are low in theta more likely to insert distractors than others?
Yeah.
So that way they're not ordered per se. Are the right answer, the right answer?
Yeah. And the D parameter, which is the intercept, will tell us when theta equals 0, the probability, the logic. So we can see for the technology one, when theta equals 0, the category 3 is the highest, has the highest probability. So the D3 for technology item will be the highest for the technology. Oh. This is D2. D2 represents option 3. So the D2 will be the highest. So option 3 will be the highest when theta equals 0. The probability and the logic will be the highest for the option 2, option 3. Which one?
The actual response option.
No.
Yeah, this is from the Mer Package, right?
Yeah, the Mer Package actually, the author said he considered the MERT, but he thinks that for multi-dimensional, he would like to use this model because each for the two, for example, 2 factors, they will share like the overall slope for each item. So not just each category has their own, but also there is an overall slope for each item. So he created this formula to model multi-dimensional factor. So for a category item, it will be estimated 4 slope and 4 intercept. There will be 8 free estimate for per item in the nominal response model. So it comes to semi-ordered partial credit model. So we select 7 items from a stress measure to fit the semi-partial credit model. So
So there these are real data I borrowed from actually there, because there is also missing data. So then the question is, what do you do with it?
Yeah. So first of all, I suggest to plot this distribution, because that if the one category is poorly used, the nominal response model will be extremely unstable. So look at this histogram. So for the item 5, there were only four people answered the category 1. And for the do not applicable option, they have a bunch of people answer that. So as Lisa said, M plus will ultimately set the highest option as a reference. But we reversed that so that the first option, extremely stressful, will be set as a reference. And the M plus will ultimately create a set of dummy coding to estimate 5 submodels for 6 category items. So there will be not applicable category versus extremely stressful, and category 5 versus 1, 4 versus 1, 3 versus 1, and 2 versus 1. So we actually will fit the nominal response model for this item, but with some model constraint. First, as we said in the nominal response, they will estimate 5 factor loading and 5 intercept. But because we want to trick the nominal response to fit the ordinal response, so that we should constrain the factor loading for the 3 versus 1 and the 4 versus 1 to equals like this. So the lambda 2 is 3, the category 3 versus 1 submodel's slope. And lambda 1 is the reference submodel, which is 2 versus 1. So the slope for 3 versus 1 is 2 multiplied by the slope for 2 versus 1. And the slope for submodel 4 versus 1 will equal to 3 multiplied by the slope of the reference submodel. Mm-hmm.
More special characters. When you have a nominal outcome, M plus refers to each of the submodels with a tone sign as opposed to the color sign. So note that we have different loadings for a single item. So CSR1 has 1, 2, 3, 4, 5 loadings for its 6 categories. And we have labeled them in backwards order to try and reverse coding. So I contacted the author of this paper that I gave you guys to read, and I asked her why she did this, and she said it was the only way she could think of to get around this constraint that M has, that the highest is the reference. She wanted the lowest to be the reference. So she flipped the data, and then basically all the labels that we're using is going to flip it back to the right order.
Yes. If we use the original response, the NA category will be the reference. So we reverse that. And we also reverse label the intercept, so that intercept 5 is intercept for NA category versus the first category. So here's the constraint for the slope. And for the NA category versus the the first category submodel, the intercept and the slope is freely estimated. So there is no constraint for that submodel. Because the NA category is not constrained to at the order of the Likert scale. So, and we create the new parameter step, which is, there is an arrow here. So this is the location at which they have people will have more likely to choose the higher category. They are not necessarily be 50-50%, but they have the same probability to choose, for example, category 1 over category 2 over category 1. It's more code. So the factor mean and the factor variance are set to fixed to 0 and 1. And here's the constraint for the factor loading.
So hang on, let's make sure that we're following here. This is non-trivial. This took us like all semester to figure this out. So the loading thing, what we're doing is we're tricking the first 5 options to one side as to be a partial credit model. So the partial credit model says that basically you have equal loading in transitioning from 1 to 2 is 2 to 3 is 3 to 4 to 4 to 5. So to get from 1 to 2, that's 1 loading. To get from 1 to 3, that's 2 loading. To get from 1 to 4, that's 3. And that's what those multiplications are then doing, is setting up the different loadings for the different submodels to all be consistent with as if we had a partial credit model that has 1 loading running through 1 to 2 to 2 to 3 to 3 to 4 to 4 to 5. And then the last one, that is just that not applicable, that loading gets to be whatever it wants. So it's that versus the highest category as a reference.
So using this method, we tell the MPath to treat the Likert scale as some predetermined order, so that if we set the 2 versus 1 as 1 unit, the 3 versus 1 will be 2 units. The 4 versus 1 will be 3 units. So here's the formula for step. The step is, as I said, is the location of the treat, so that someone will have more likely to choose a higher category. So for example, step 1 will be the treat that someone will more likely to choosing category 2 over category 1. The step 2 is choosing the more likely to choosing category 2 over category 3 over category 2.
So we're subtracting the intercepts because that's how they're defined in the nominal model. In the nominal model, it would be, what, 3 versus 1 and 2 versus 1.
1.
So to get 3 versus 2, subtract the difference there. Otherwise, it's the same as the p-values that you're using, which are the threshold over loading. That's what the -1 there does, because nominal is raised to intercept instead of threshold, so we're flipping the direction back to the partial credit model. And the rest of that, you don't actually need to pay attention to. That's just me making sure that we got everything right.
Let's look at the parameters. So here's a predict category. I use this table to plot the category response. This plot is reversed order.
Yeah. Let's look at the next one down. This is back to the original order.
Yeah. So the NA category is the lowest option.
Well, NA is not ordered, right?
Yeah, it's not ordered.
Yeah. So the pink one. The pink one is the extra one that we get from doing all this fancy code.
Yeah. So that we can see the items 5 and X6. The pink one is not in the left hand of the plot. So the NA category It's not necessarily be ordered at the lowest option.
Yeah, so it looks like the extent to which NA is useful varies by item. Like if you look at 4, NA shows up on the lowest end, whereas like 5 and 6 is just creeping along the bottom, and it doesn't appear to be very related to the trait at all. But you can actually test using this methodology to what extent not applicable, answering that instead of these other categories is indicative of the trait you're trying to measure. That's directly what the loading is going to tell you. Is the probability of selecting not applicable instead of these others, is that related to theta? If it's not, your loading is close to 0, and it just, you get this flat thing. And if it is, then you can judge how steep it is as well as the location of it. So it looks like it's easier to say does not apply than applies, that bothers me a little more than a little, et cetera, et cetera. So it kind of makes sense in the way I think they conceptualize it, that not applicable is the lowest. Because if this thing doesn't apply to you, then it's not a problem for you. But that may not be true in other situations in which not applicable really is like outside the realm of ordinal categorization.
So here's the parameters for NA category. This actually is a submodel for NA category versus category 1. You can see the item 1's NA category has the highest discrimination. Yeah, so this, I would say the NA category versus 1's slope is quite steep. That's why the slope is the discrimination is very high. And you can see these two items are, the NA category is very flatter. Here's the item information curves for 7 items. I plot this by sum up all submodel information. So for each item, there are 5 submodel information. So for example, item 1, the information is sum up 5 submodel information together. From this plot, we can see the item 5 has the highest information. And item 2, item 7, item 1 is very low, has low information. Sum them up is the test information. We better look at the reliability. Reliability is information divided by information plus 1. We can see from -1 to 2 has a probability above 0.8. But I have an error here because the theta doesn't mean the strength, because we reverse order the item's response. So higher theta means less strength. So minus, yeah. So minus 1.8 to positive 1. Minus 1.8 to positive 1 will be the highest reliability. Highest reliability, yeah. For this information, for test information.
Yeah, what direction of theta is high stress, which direction is low stress?
So for this direction, so 1 theta higher, that means less stress. I can like to reverse this plot. It's like to multiply by -1. Yeah, the model goes the wrong way. Yeah. Yeah. I would say for this test will be reliable for the middle-age student, middle-age stressful student. That's all. Any comments, suggestions? So I can also interpret the steps for example, the category 1 versus category 2. The step parameter is 4.5. So in theory, the predict probability will be same when the theta equals 0.8. The probability for category 1 versus category 2 will be same. So we can look at the predicted probability for category 1 and category 2. So look at the theta equals 0.5. They got almost the same predicted probability to choosing category 1 and category 2. So this what the step means. So this location of the trait when you have more likely to choosing the higher category versus the lower category.
So to get from 1 to 2 for item 7 here, So the next one over 1.1 is the amount of theta you need to pick 4 instead of 3, and then finally 1.8 is the amount of theta you need to pick 4 instead of 5. So the same concerns about these things being on top of each other applies here. It looks like there's a big jump to go from like step 1 to step 2, but then to go from 2 to 3 is not very much. So those locations are not as discrepant from each other on the trace as it is to go from, say, 4 to 5. That's a big jump relative to the third step 3 versus step 4. So the nominal model says that every item gets some intercept and its unloading per submodel. We just fit constraints on this so that it follows the partial credit model setup. In the meantime, we let the answer for not applicable versus the first category just do whatever it wants. It gets its own loading and it gets its own p-value. So can we go to those? Yeah. So the discrimination then for not applicable versus one. So basically this submodel controls whether you answer not applicable or 1. And then the next submodel controls 1 to 2 to 3 to 4 and 5. Like it's sort of like 2 chunks of an item. And so for this one, say, the last item here, the discrimination is 5. That's pretty strong. The difficulty is 1.3. So it takes a theta of 1.3 is where you have a 50-50 shot of moving from not applicable to at least a 1. And then the rest of the model takes over and talks about where you go from 1 to 2 to 3 to 4 to 5. So the extent to which those discriminations are greater than 0, that tells you literally whether you are throwing information away by taking the not applicable out of the model. And on that note, it might also be informative if you have questions where there's a lot of missing data, to think about treating missing data the same way. If people deliberately didn't answer certain questions, that's not missing at random. So if you chose not to answer, right, whether they picked that box or just didn't fill in any box, chose not to answer, could be treated just like not applicable in the same way.
So it's very easy
Well, political ideology was an example of just a nominal type of response item.
right, but in a lot of the okay, yes, you identify as Republican, Democrat, Independent, whatever it happens to be. But that's not happening. So the idea is upfront identify.
Well, so an item like that.
Blatant activity, conservative thinking, liberal
Yeah, so like you had statements that you had to say, like pick which of these statements best apply to me kind of thing, right? Then that would be the kind of item that would go along with your self-labeling, trying to indicate some sort of trait. Where you could say that people, low in theta tend to pick these 2 statements, people high in this trait tend to pick these 2. So yeah, there's like those types of pictures. Yeah, those ones. For instance, like I'd say people who are low in this trait pick pink or green dots. People who are high in the trait tend to pick red. And if you're not going to pick red, you're going to pick blue a little bit more often time than you pick the others. That kind of thing.
would want to make it so that the first, I guess, 5 items, basically the nominal items, or no, they're ordinal. The ones that are ordered, basically, that everything but not applicable.
Mm-hmm.
What's the benefit of making them like partial credit as opposed to doing this like like everything was nominal and giving all of them a loading and intercept?
I think the advantage is we pretty sure like the Likert scale like have some kind of order, so we want to give it some information to nominal response to treat it as like, for example, strongly disagree is a lower option than disagree. So this is like we design these items. Our theory like tells us if we want to use a Likert scale, we have some kind of order. Instead of like the first item, we like which party you are identify. We have no predetermined order underneath, so we just use the nominal to tell us at which trade you are more likely to choose which category. But in the ordered response, we have some kind of order information behind. That's my understanding.
Well, and practically speaking, it's a number of parameters.
Mm-hmm.
So each of these 7 items is going to have 2 loadings and 5 intercept like things.
Yeah.
If you want to go full nominal, then you have 6 loadings per item, along with 5 loadings per item, and 5 intercept like things.
Yes. So
that's a lot more.
Yeah, we can calculate the total parameter for each item. There are 2 loadings and 5 intercepts, so there will be 7 parameters per item. For a 7 item measured, there will be 49 total free parameters. But if we estimate the nominal response, there will be 5 slope and 5 intercept, so 10 parameters per item, and then 7 items will be 70 total free parameter.
Can you show the infographic?
Mm-hmm.
So, like these ones where there's nobody down here, you're going to try to put a slope on like 70 versus 100 and whatever, while it's blow up. What if it was a tremendously large sample? Let's say you had 1,000 people and even the smallest category has 75. Then go for it. Okay. That's not the world I live in. Okay. But yeah, practically speaking, you have to have enough information to estimate the slope and the loading and the intercept for each separate category. And there's tremendous savings in going to partial credit because they share the loading.
Yeah, as I said, if one category is poorly used, the nominal response model will be extremely unstable.
I think in theory, whether you can constrain the loadings to be the same,
yeah,
should be testable, right?
Yeah, I think it should be testable.
Because partial credit would be nested in nominal.
Yeah, I think so.
Any other questions? Can we give him a round of applause for being brave enough to stand up?
Thank you.
Yes, thank you. We've been looking at this all.
So in the few moments that I have left, I want to give you sort of a broad overview here, because we're changing gears in the next class. So we've talked about basically 3 kinds of data at this point. We've talked about continuous data, right? Continuous responses, that's CFA. Binary data, that's IRT or IFA. And categorical data. Categorical is also called polytomous, where you can have ordinal, nominal, or some combination thereof via these models. But then what if you have something else? What should I have done in my dissertation, for instance? Why did I cut up response time? Because I wanted to do IRT, and I didn't know how to do IRT for these types of data. What would I have done instead is lecture C, the one that I posted the video from 2016 because I knew that we wouldn't get to it. The idea that all of the other kinds of regression models and distributions are at your disposal in this world of, what do you call it, types of item responses that you can throw a measurement model at. So for instance, if you have a count, you can fit Poisson-like measurement models where you predict the log of the count. If there are too many zeros or not enough zeros, you can augment them. You can also fit things that are called hurdles or two-parts, which is actually what I should have done in my dissertation. So these are helpful for situations in which you have potentially missing data that's informative, like what I had. So in my task, I had people do a search task, and they only had 45 seconds to complete the search task. If they didn't find what they were looking for, I counted it as incorrect. So each trial was characterized by two DVs, whether they found it and how fast they found it, if so. And I didn't know what to do with that combination of things, so I didn't find it, found it right away, found it after a little while, and then found it long time. Right? That's all I knew how to do, and they let me graduate. Don't take my PhD away. That's what I knew how to do in 2003. I now know I should have done something like this, two-part, where you literally fit a binary indicator for an instance, did they find it, and then a second continuous indicator for how long it took them. And these can load onto the same factor or different factors. So this is how I would have treated continuous data that had this extra hurdle in terms of answers not being observed. Here's another example. This is a master's thesis that I helped get published in, I forget what journal this is, Journal of Child something or another. This is a task in which adolescents are told they have to get to a party as fast as possible. And at each trial, they can either decide to break when a yellow light happens, or they keep going. And apparently everyone who had used this task before, if they decided to break, then treated their latency to hit the brake as missing. Or if they didn't decide to break, excuse me, I have it backwards. If they kept going, then they didn't break, that was missing. Like, that's not missing. That's like the definition of the trait. So I helped him fit a two-part model where we had whether or not that the adolescent decided to go as one binary indicator, which you now know how to do, and their latency to break if they decided to break on a separate factor. And it turned out that that latency or that decision to go was the only thing that predicted his risk outcomes later on. Whether or not they decided to break was the big ticket item, not how long it took them. So had we coded the data in the way that typically is done, we would have missed the whole story. So point being, if you're ever in a situation in which you have a trait that's indicated by data and you don't know what to do with it, there are models out there. You don't have to try and shove it into a CFA or an IRT or an IFA. Let me help you find something, okay? Deal? You'd be surprised at how many creative things people have come up with. So we're switching gears then starting on Wednesday. We're going to start talking about invariance, which first in the CFA framework and then in an IFA framework, the question of whether or not your items are measuring their trait in the same way across groups of people or across time. To what extent can your scale be used in different populations with the same intent? That's the question. And it's a series of nested model comparisons. There's nothing new other than adding model constraints and testing whether or not things get worse. That's going to be the big deal. So we will have that on Wednesday. Any questions before we adjourn? All right, then office hours start now. I will see you in a few days.